Hello student, we are going to start our session Digital Image Processing EC703A Module 5 Lecture 2. Sangita Roy, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. Content: Edge detection in digital image processing. Types of edge detection, mathematical equation of each operator. Modeling intensity changes. Edges can be modeled according to their intensity profiles. So this is an image and corresponding intensity profiles, and it is noisy image and it is intensity profiles. For step edge, the image intensity abruptly changes from one value to one side of the discontinuity to a different value on the opposite side. Rampage, a step edge where the intensity change is not instantaneous but occur over a finite distance. Ridge edge, the image intensity abruptly changes value but then returns to the starting value within short distance, gradually, usually by lines. So this is ideal one and it is corresponding noisy one, and this is another ideal one and it's noisy image. Roof edge, a ridge edge where the intensity change is not instantaneous but occur over a finite distance, generated usually by the intersection of surfaces. So it is a roof edge, very sharp change over there, it is a quite flat change, and it is noisy output. The 4 steps of edge detection: smoothing, enhancement, detection, localization. Smoothing, suppress as much noise as possible without destroying the true edges. Enhancement, apply a filter to enhance the quality of the edges in the image, also known as shortening. Detection, determine which edge pixel should be discarded as noise and which should be retained. Usually thresholding provides the criteria used for detection. Localization, determine the exact location of an edge. Sub-pixel resolution might be required for some applications. That is, estimate the location of an image to better than the spacing between pixels. Edge thinning and linking are usually required in this step. Edge detection using derivatives. Calculus describing changes of continuous function using derivatives. An image is a 2D function, so operators describing edges are expressed using partial derivatives. Points which lie in an edge can be detected by detecting local minima or maxima of the first derivative and detecting the zero crossing of the second derivative. Thus, first derivative gives edge, whereas point can be identified by zero crossing second derivative. Differencing first derivative signals. So, to compute the derivative of a signal, we approximate the derivative by finite differences. So, the first derivative is given by according to calculus. So, this can be represented by mask as -1 and 1. Example using the edge models and the mask -1, 0, 1 centered about x. So, this is an example. And the second derivative is given by according to calculus this, and the approximation centered about x plus 1 replaced by x plus 1 with x is given by f double dashed by this. So now the mask become, earlier the mask was -1, 0, 1. Now the mask become 1, -2, 1. And this is an example showing how the localization is finding out over there in a edge. Example using the edge models. So this is a kernel or mask -1 to -1 and how the changes occur, it is showing over there. And this also we have discussed in the segmentation section also. Edge detection using the gradient. Definition of the gradient, we have already covered this one. So this is given by the gradient, and also the angle given by tan inverse my by mx, and magnitude by mod of x, magnitude of x and mod of magnitude of y. Now the properties of the gradient. The magnitude gradient provides information about the strength of the edge. This is the direction, and this is the normal of a particular pixel has taken in an edge, and corresponding direction of edge and its normal edge also showing. So estimating the gradient with finite differences according to calculus, this is coming. The gradient can be approximated by finite differences by this. This is calculus approximation, and this is finite differences. Now this is a notation in the pixel coordinates. This is along x-axis and along y-axis. X is the center over there. So if we go on like this, it will be x plus h, x plus 2h and on. And if we go in this way, it will be x minus h, x minus 2h on. Similarly, as for y, if we go upward, x plus h, y plus h. If we go down, y minus h. And corresponding del f del x is given by this, and del f del y is given by this. Thus, if it is a filter mask, then di by del partial, this is obviously partial, del I by del x is equal to z6 minus z5, del I by del y is equal to z5 minus z8. Therefore, magnitude of this is equal to given by this, and del I del x is given by minus 1 by finite approximation, and del y by del y, del I by del y is given by 1 minus 1. These are the references. So before thank you, we will do again MATLAB. So it is not a, it is showing some edges without any kernel, fixed kernel that is inbuilt in MATLAB. It is given by some coefficient kernel. So cameraman tip has been taken. First one, it is showing for vertical edges. Then it is for horizontal edges, this one for horizontal edge. Then diagonal edge, corresponding mask. Then combining all secondary diagonal edges given by this, and final edge detection is given by this. So first, horizontal mask or horizontal kernel is given by 1 0 minus 1, 1 0 minus 1, 1 0 minus 1. And for vertical kernel, it is 1 1 1 0 0 0 minus 1 minus 1 minus 1. And for diagonal, principal diagonal, it is 0 minus 1 minus 1. This is 1 0 minus 1, 1 1 0. Then secondary diagonal, 1 1 1 0 0 0 minus 1 minus 1 minus 1. And finally, the edge detection will be the combination of all these masks. So if we run the program, so 5 images will come obviously, horizontal, vertical, diagonal, secondary diagonal, and final edge detection. So it is the horizontally, if the filter kernel is horizontal, then it will be like this. If it is kernel is vertical, if it is diagonal, if it is secondary diagonal, it is like this, and combination of all this is given this. So thank you. This is all about today's class.